Topology is a branch of mathematics that studies the shape and structure of objects, but in a very unique way. Instead of focusing on exact measurements like length or angles, topology looks at how different parts of a shape are connected to each other. It studies how a shape can be stretched, twisted, or bent without cutting or tearing it. For example, imagine a rubber band. You can stretch it, twist it, or even squish it into different forms, but as long as you don't break it or glue parts together, it's still considered the same in topology. This helps mathematicians and engineers understand the deeper structure of objects, beyond just how they look on the surface. Another example, a donut and a coffee mug are considered the same because they both have one hole. This is because you can reshape one into the other without cutting or gluing. So, what is topology optimization? Have you ever looked at a bird's wing or a tree branch and wondered how nature creates structures that are both incredibly strong and astonishingly lightweight? What if engineers could design machines the same way, using artificial intelligence to mimic nature's efficiency? Imagine excavators, aircraft, or bridges built with less material, yet performing better than ever before. Topology optimization is a computational design method that determines the best way to distribute material within a given space, under specific loading conditions. In simple terms, it helps engineers figure out where material is truly needed and where it can be removed, based on the loads, forces, and boundary conditions acting on a part. The ultimate goal is to make a component as light as possible while maintaining strength, stiffness, and performance. Instead of starting with a fixed shape, engineers define a design space, which is usually a solid block or volume, apply loads and constraints, and gradually removes unnecessary material, keeping only what's essential for structural integrity. The result is often a skeletal, organic-looking geometry. Strong where it needs to be, and hollow where it doesn't. Let us dive into the detailed process of topology optimization. The process is driven by mathematical algorithms and finite element analysis, or FEA, ensuring that the resulting geometry can withstand real-world forces efficiently. Engineers begin by specifying the region where the part can exist. This includes the external dimensions, mounting points, and areas that must remain solid or open. The forces, pressures, or loads acting on the part are applied. Fixed supports, connection points, and other physical constraints are defined. The objective might be to minimize weight, maximize stiffness, or reduce displacement. Constraints such as maximum stress, deflection limits, and manufacturing restrictions are added. The software uses iterative FEA simulations. In each iteration, it removes material from low-stress regions and reinforces high-stress areas until an optimal shape is achieved. The final output looks like an organic, lattice-like, or skeletal structure, often irregular and curved. Engineers then refine this model into a manufacturable CAD design, ensuring it meets manufacturing and assembly requirements. Now, let's explore how artificial intelligence helps in bringing this optimization to the next level. I believe you have already heard about machine learning. Machine learning and artificial intelligence are transforming topology optimization by making it faster, more efficient, and capable of handling complex design challenges. Here's an overview of their roles. Traditional topology optimization methods rely heavily on finite element analysis, FEA, and iterative solvers, which are computationally expensive and time-consuming. ML models, especially deep learning algorithms, can learn from previous optimization results and predict optimal material layouts much faster, reducing the need for repeated simulations. Some studies report speed-ups of up to 30 times compared to traditional methods. AI can create surrogate models that approximate the behavior of complex physical systems. These models replace the need for solving detailed physics equations in every iteration, allowing for rapid evaluation of design alternatives. By training on large datasets of optimized structures, ML models can generate new, high-performance designs without needing a predefined shape. This opens up possibilities for creative and non-intuitive solutions that traditional methods might miss. Some AI approaches aim to bypass the iterative process entirely. For example, convolutional neural networks can be trained to directly output optimized designs based on input conditions like loads and constraints, enabling real-time design generation. AI helps manage large-scale and multi-scale optimization problems by learning patterns across different scales and geometries. This is especially useful in fields like aerospace, automotive, and biomedical engineering, where designs must meet strict performance and weight requirements. These AI-generated designs often resemble biological structures, curved load paths, branching supports, and smooth transitions that reduce stress concentrations. They're not just visually striking, they're mechanically superior. For example, in heavy equipment like excavators, AI-driven topology optimization has led to boom arms that are up to 30% lighter, while maintaining or even improving strength and fatigue life. This translates to better fuel efficiency, faster hydraulic response, and increased payload capacity. Researchers are exploring physics-informed ML, transfer learning, and hybrid models to overcome these limitations and make AI-driven topology optimization more robust and reliable. Now you got the optimized three-dimensional model, but how do you manufacture something that looks more like a bone than a beam? That's where advanced manufacturing comes in. Engineers use hybrid manufacturing techniques, combining casting, forging, and additive manufacturing, 3D printing, to bring these complex geometries to life. For instance, a boom arm might be cast for its main structure, with 3D printed titanium reinforcements inserted into high-stress zones. Robotic welding systems, guided by offline programming tools, ensure precision assembly without the need for custom jigs. Additive manufacturing plays a key role, especially for components with internal lattice structures or intricate geometries that traditional methods can't produce. Technologies like selective laser melting, SLM, and electron beam melting, EBM, allow engineers to fabricate parts layer by layer, using high-strength alloys like Ti6Al4V or 7075 T6 aluminum. These materials offer excellent strength-to-weight ratios but require careful post-processing, heat treatment, surface finishing, and non-destructive testing to ensure durability. So, what does this mean for the future of engineering? Are we entering an era where machines evolve like living organisms, optimized not by trial and error, but by intelligent algorithms that learn and adapt? Could this be the key to building smarter, stronger, and more sustainable technology? If you're curious about how AI is reshaping the way we design and build the world around us, you're not alone, because this isn't science fiction, it's happening now, and it's changing everything.